This is a video from section 12.3 and it's based off the lecture notes. We're going to start off with a definition. If A is the vector A1, A2, A3, and B is the vector B1, B2, B3, then the dot product of A and B is the number A dot B given by the following formula. A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. And so to get the dot product, we took the first component of A and the first component of B and multiplied them. Took the second component of A and the second component of B and multiplied them. And then we took the third component of A and the third component of B and multiplied them and then proceeded to add the results. Okay, now, although the definition is given for three-dimensional vectors, the dot product of two-dimensional vectors is defined in a similar way. So, in other words, if A is the vector A1, A2, so this is a two-dimensional vector, and B is the vector B1, B2, then A dot B is A1, B1 plus A2, B2. And we're going to go ahead and take a look at a couple of examples. So suppose A is the vector 5, negative 2, and B is the vector 3, 4, and we want to find A dot B. So A dot B is equal to 5, negative 2 dotted with 3, 4. And this is 5 times 3 plus negative 2 times 4. And so this is 15 minus 8. And so if we continue on over here, 15 minus 8 happens to be 7. So in this example, A dot B is equal to 7. Example 2, suppose A is the vector 6, negative 2, 3, and B is the vector 2, 5, negative 1, and we want to find A dot B. Well, A dot B is 6, negative 2, 3, dotted with 2, 5, negative 1, which is equal to 6 times 2, right? Because I took the first component of A and the first component of B and multiply them, plus negative 2 times 5, plus 3 times negative 1, which is equal to 12 minus 10 minus 3. And so if we finish this problem, it looks like A dot B is equal to negative 1. That's example 2. For example 3, A dot B is equal to P times 2Q plus negative P times Q plus 2P times negative Q, which is equal to 2PQ minus PQ minus 2PQ. So if you notice how the 2PQs cancel, right? And what that tells me here is that A dot B is equal to negative PQ. And that's how we do example 3. The dot product obeys many of the laws that hold for real numbers. Okay. Now, suppose A, B, and C are vectors and K is a scalar. Let's look at property 1. A dot B is the same as B dot A. Property 2. If I take KA, so in other words, if I take a scalar multiple of A and dot it with B, that's the same thing as taking K times the dot product of A and B. And in fact, it turns out that's the same as taking A and dotting it with the scalar multiple of B. So we call that property 2. Number 3, we have a form of the distributive property. So if I take A and dot it with the sum of B plus C, that's the same as A dot B plus A dot C. Number 4, A dotted with itself. So if I take the dot product of A and A, I get the magnitude of A squared. Number 5, if I take the 0 vector, so in other words, a vector that's comprised where all the components are zeros, right? So if I take 0 and dot it with A, I get 0. So this 0 on the other side is a scalar. The 0 over here that I'm pointing to is a vector. So there is a difference. We're going to go ahead and take a look at the proof here for 3 of the properties. Now, let A equal the vector A1, A2, A3, B equal the vector B1, B2, B3, and C equal the vector C1, C2, C3, and let K be a scalar. And we're going to look at property 1. So we're going to take a look at the dot product of A and B. So these can all be verified with the definition. So A dot B is equal to the vector A1, A2, A3, dotted with B1, B2, B3. So from the definition, that means we get A1, B1 plus A2, B2 plus A3, B3. But the real numbers commute, right? So in fact, this is equal to B1, A1 plus B2, A2 plus B3, A3 right here. And then we can unwind it. And so this is equal to the dot product of the vector B1, B2, B3 with A1, A2, A3. But this is equal to B dot A. So we have just shown that A dot B is the same as B dot A, and we have commutativity. Let's take a look at the proof of property 4. If I take A and dot it with itself, that's equal to the vector A1, A2, A3 dotted with A1, A2, A3. But this is equal to A1 squared plus A2 squared plus A3 squared, which is equal to the square root of A1 squared plus A2 squared plus A3 squared squared. But remember, the length of A, in other words, the magnitude of A, is equal to the square root of A1 squared plus A2 squared plus A3 squared. And so the square root of A1 squared plus A2 squared plus A3 squared is equal to the magnitude of A squared. And we have just shown that A dot A is equal to the magnitude of A raised to the second power. And that's property 4. Property 5, if I take 0, the vector 0, and dot it with A, I get the vector 0, 0, 0, dotted with A1, A2, A3. That's right here, where I have check marked. But by the definition of the dot product, I get 0 times A1 plus 0 times A2 plus 0 times A3. But this is equal to 0 plus 0 plus 0, which is equal to 0. So 0 dotted with A is equal to 0. Now remember from property 1 that 0 dot A equals A dot 0. So we have vectors that commute, right? And so that will verify that A dot 0 is also equal to 0. So we have that automatically. Okay, let's continue forward. We're going to look at a theorem. If theta is the angle between vectors A and B, then the dot product of A and B is given by the magnitude of A times the magnitude of B times cosine of theta. One thing I want to make note of here, so let's put a note. We want theta to be between 0 and pi. Okay. Now, let's take a look at the proof. And if you notice, I have a picture here. So here's vector A, highlighted in blue. Okay? Here's vector B that I'll highlight in red, right here. And I claim if I go from here to here, I get vector A minus B. So I just let C equal the difference between vectors A and B. All right, now, so what we're going to do is we're going to apply the law of cosines. And it says the following. If I take the length of A minus B to the second power, this is equal to the length of A squared, or the magnitude of A squared, plus the magnitude of B squared, minus 2 times the magnitude of A times the magnitude of B times cosine of the angle between the vectors. Now, we're going to calculate the magnitude of A minus B squared in a different way. So if I take the magnitude of A minus B and square it, remember from those properties that that's the same as A minus B dotted with A minus B. Now I'm going to distribute this out, okay? So I get A dotted with A minus A dotted with B, right? So in other words, I get A dot A minus A dot B minus B dot A, right here, plus B dot B. But remember that A dot A is the magnitude of A squared. B dot B is the magnitude of B squared. And remember that A dot B is the same as B dot A. So on this line, second from the bottom, we get the magnitude of A squared minus A dot B minus A dot B plus the magnitude of B squared, which is equal to the magnitude of A squared minus 2 times the, I'll say it this way. You get the magnitude of A squared minus 2 times the dot product of A and B plus the magnitude of B squared. And so now we can set those results equal to each other. And that's what I did over here. So I took the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B cosine of theta. And I'm going to set that equal to the magnitude of A squared minus 2 times the dot product of A and B plus the magnitude of B squared. So what that tells me is that negative 2 times the magnitude of A times the magnitude of B times cosine of theta is equal to negative 2 times the dot product of A and B. Why? Because if you notice, the magnitude of A squared cancels, right? Because we have the same thing on both sides. Same with the magnitude of B squared. They cancel because we have the same term on both sides. If I divide both sides by negative 2, I've proven the result. And so we have to assume law of cosines to prove this dot product formula. Or if you want to prove the law of cosines, you have to assume this dot product formula. So it works in reverse. But the assumption of one will prove the other result. And that's going to conclude this video for section 12.3. And again, this is part 1. And this video is based off the lecture notes. Thank you.